So this video is going to be on Bayes' theorem, which is a pretty important probability concept and theorem that um, is used quite often, especially in medical testing and uh, figuring out the effectiveness of certain tests and whatnot. So again, it's going to sound really strange at first, but there is a sort of easy repetition with the formula, as you'll see when we do a problem or two here. Um, so just make sure my mic is actually on here. Okay. Again, always get worried that my mic is not on. Um, so Bayes' theorem stated directly is just like what you see here. Basically, it's a way to get conditional probability in. So the probability of A happening given B happens is the probability of B happens given A happens times the chance that A happens divided by the chance that B happens. So it's very similar. In fact, it's just a version of the normal conditional probability stuff we did in the past video. Because if you notice that this part right here is basically just the probability of A and B. That's the breakdown version of the probability of A and B happening. So it's usually stated in this way, and again, you'll see why we usually state Bayes' theorem in this version rather than saying probability of A and B on top in just a second. But first, just to make sure I state the importance, because Bayes' theorem is a very, again, like I said, a prestigious sort of theorem in stats. It's often described as basically Pythagorean's theorem for statistics. So Pythagorean's theorem is a very important and key concept in geometry that kind of unlocks a lot of the other stuff in geometry that we can use. Bayes' theorem does that same thing for statistics. So it's a very key cornerstone topic in probability theory. Um, so let's see in action here, or kind of how it's used there. And again, medical testing and gauging the effectiveness of certain medical tests is what it's really known for. So basically, when you have let's say you have a virus, or you might have a virus, and you want to develop a test to see if you do, or if you're a doctor, you want just to see if you can develop a test that will scan if somebody has been exposed to a certain, say, pandemically influenced virus. Not to hit the nose, or not to hit the nail too on the head there, but basically, when you take a medical test, there's four outcomes that can happen, not two, but four. You can either test positive and have the virus, which is called a true positive, which means basically the test worked. You can have a positive result but not have the virus, because again, tests aren't 100% accurate. So that's called a false positive, where the test says you do but you actually don't because of some error or flaw in the testing. Um, it comes up as a false positive. This is usually a very bad thing. You can test negative and actually have the virus, which is a false negative. So again, due to some flaw in the testing or slip up or whatever, you take the test and it says you don't have the virus, but you actually do. That is a very bad thing to happen. Probably even worse than this one. And then the last one is you test negative and you don't, which again is called a true negative because again the test worked. You didn't have the virus, it says you didn't, everything agrees. So Bayes' theorem says, okay, let's say you take the test and you test positive. Bayes' theorem allows you to see how likely it is that you actually have the virus. Because if somebody comes out and says, well, this test is 90% accurate, meaning that usually when they say that, they mean that if you have the virus, this test will catch it 90% of the time. So if you have the virus and you take the test, it will show you that you have the virus 90% of the time. But that doesn't mean that it's 90% accurate per se. That doesn't mean that if you test positive, there's a 90% chance you actually have the virus. And we'll see why that is here in this next problem, actually. So let's kind of go through an example of this. So let's say we have a virus and they develop a test, and the test is what we call 90% sensitive, which means that 90% of the people who test positive do actually have the virus, which means it's a 90% true positive rate. That 90% of the positive results are from people who actually do have the virus, which again, by extension, means that 10% aren't. Um, and 80% specific. So 80% specific is what normally gets lost in translation. So people will see this and they say the test is 90% accurate, which is not quite true because it can be 90% sensitive and 80% specific, which means that 80% of the people who test negative don't have the virus, which is the true negative. But if you take that meaning here, that means that 20% of the people who test um, give a false positive. So that means that 20% of the people who take the test and the test comes back and says, hey, you have the virus, that's wrong. That's a false positive flag there. And this is what normally does not get reported because, again, they're so focused on the sensitivity part of it. And also Bayes' theorem, again to be accurate here, has to take into account the overall probability of getting the infection in general. So let's say that, again, based on past studies and cases, we find that 5% of a population can be considered infective. So we're like 95% sure, again, doing our confidence intervals, we're 95% confident that 5% of the population is infected with the virus. So again, it's a pretty rare virus that if only 5% of a population has it, given a decently sized population. So let's say you take this test, or a person takes this test, and it comes back positive. Well, how likely is it that they actually have the virus? Let's say this is a deadly virus, and if you have it, you're going to certainly die. You obviously want to know, okay, the test gave me a positive result, but it also has a 20% false positive rate, and the virus is also very rare. So that doesn't mean I'm 90% certain to have it. It's actually a little bit less, or maybe a lot less. Let's see, actually. So what we're looking for is this probability, right? The probability that we're infected given we tested positive. Okay? So we already know we tested positive. We want the probability now that we're infected. So infected given that we're positive. So according to Bayes' theorem, the probability of this happening is the probability that we test positive given that we're infected, so the reverse. So this is the probability that if we assume we're infected, how likely is it that we test positive, times the chance of us actually being infected, divided by the chance of us actually testing positive. Now, the problem is that we know some of this, but not all of it directly. So we know that the chance that we're infected is about 5%, because again, it says 5% of the population is assumed to be infected. So if we are infected, we're going to count ourselves among that 5%. So we know that the infection rate, or the infection percentage, proportion, whatever you want to call it, is 5%. So this right here is 0.05. We know that much. We also know that the chance that we test positive given that we're infected is 90%, because that's where that 90% true positive rate comes into play. Because remember, it says up top here that's 90% sensitive. So 90% of the people who test positive do have the virus, which again is just a fancy way of saying 90% is the probability of positive test given that you're infected. So this right here is 0.9. But we don't know what this is or what this is, which is a problem because in math we usually want to know all but one piece, because if we're missing one piece we can solve an equation to find that missing piece there. But if we have two pieces missing, that becomes an issue unless they're related in some way. But luckily, based on the last video, which again, if you haven't seen the last video, you should see that first because this is going to draw from that. We don't know what the probability of being a positive test is explicitly, but due to the law of total probability, we know that if you test positive, there are two cases, right? You can test positive and be infected, and you can test positive and not be infected. So we can break down this overall probability into its two components: the infected that test positive and the not infected that test positive. Those two probabilities combined is my overall chance of testing positive. So I take the chance that I'm give a true positive plus the chance that I get a false positive, and that's the chance of me testing positive in general. Now, we don't necessarily know each of these explicitly, so again, we break these down. The chance that I test positive and are infected is this probability right here. The probability that I'm positive given that I'm infected times the chance I'm infected, plus the probability for this one right here, the probability I test positive and is not infected times the chance that I'm not infected. So I break these two down into their component parts. So it's basically a double breakdown here. I break down the overall chance of being a positive result into its two different versions, negative and positive, or sorry, infected and positive and not infected and positive. And then I break these two down into their core components. So this is the probability that I'm positive given that I'm infected times the chance I'm infected. And then this over here is the probability that I test positive and am not infected times the chance I'm not infected. And so if we plug this entire mess here, if we plug that entire thing back in for the denominator in our little Bayes theorem fraction, we end up getting this right here. So this is my top piece of my Bayes theorem, positive given that I'm infected times the chance I'm infected. And then my bottom piece is these two combined probabilities I just talked about. Now, once we break it down to this version, now we know all the pieces. So now we actually can complete this fraction here, because we know that positive, given that you're infected, is a 90% rate there, because this is a true positive result. Probability that you get a true positive, which means you test positive and you're infected, or given that you're infected. So we have 0.9 for the true positive rate, times the infection rate, which we said was 0.5 because 5% of the population is infected, so 0.5 or 0.05, not 0.5. Then this part right here, if you notice here, this part is just the same as this part. So this basically just gets copied twice, which means that this is usually how Bayes' theorem is kind of written, and people look at it and they think that's a really big, long, complicated formula, but half of it's the same. Like these two entire chunks here are the exact same. So zero point 0.9 times 0.05. So most of it's just a repetition. And then the last part here is simply the opposite of these two. So this is the probability that you test positive given that you're infected. The next one's going to be the probability that you test positive given that you're not infected, which again we know is um, actually that should be 0.2, right? Almost lost my place there. So 0.2, because there's a 20% false positive rate times the chance that you're not infected, which is 0.95. So if we plug this big mess of a fraction in, so zero point 0.9 times 0.05 divided by zero point 0.9, whoops, let me do that in double parentheses there, 0.9 times 0.05, which is what I had before, plus 0.2 times 0.95, and we get about 0.19, or about a 19%. So that means that if you get a positive result back from your test, that means that you only really have a 19% chance of actually being infected, which is again even less than 20%. So that means that this test, if you get a positive result, isn't necessarily that reliable. And that's mainly due because even a small false positive rate, if you have a small false positive rate combined with a small amount of general infection, that can really be hard to test for. That's really hard for a test to compensate with. So you have to really work on narrowing down those false positives and improving your tests to be more uh, specific rather, or more sensitive without testing for or without catching any false positives there, which again is a pretty hard thing to do in the medical field there, because again technology and stuff in that area tends to move a little more slowly nowadays because we're already pretty advanced, so kind of pushing the limits there is a little bit hard to do, especially in a pandemic state there. So this is why, again, not to get too, again, not gonna get political or anything right now, but due to current events here, this is why when people again clamor for we need more testing, we need more testing, we need more testing, well, if the tests have a decently high false positive rate, again, just a 20% false positive rate, those tests might not actually be that necessarily accurate. They might spread more panic than good there, because again, if people come back with a positive test result, well, there's really only a 19% chance that you're actually infected if you come back with a positive test result. Um, Again, think about it as like if you have a test that just 100 times, 100% of the time comes back positive. So let's say you have a test, you're testing for the virus, and 100% of the time it comes back as a positive result, whether you're infected or not. It's just a 100% chance of coming back positive. Well, you're definitely going to catch everybody who has the virus because it's a 100% chance it's going to come back positive. But you're also going to catch everybody else who doesn't either. So it's a useless test essentially. So that's why, again, when people talk about testing and whatnot, you have to kind of take into account the fact that even in general medical testing, if it's a very rare infection and a very new infection or a very new virus, testing might not be all that good and accurate really early on. So again, you might want to go down other routes of possible mitigation here. So again, just if you do get a positive test result way on in the future for a deadly, very, very, very rare virus, and it comes back positive, don't automatically assume that you're going to be seeing the Undertaker anytime soon. Again, if the infection was more common rather than just a 5% infection for the population, then the test would be a little bit more accurate. So basically, the higher these bottom numbers go, usually the better overall it is for your stuff there. Because again, these two are always going to be the same. So if you want a test to be really accurate, you want to make sure you have a high enough infection rate that it's at least somewhat common, and you want to make sure that you have a very low false positive rate, so that you don't, again, catch the false positives essentially. So, like I said, just be wary of medical testing and taking things at face value there. Not saying medical testing is useless. It's not. I'm not trying to go down that route. But again, for very rare diseases and very rare infections, testing can kind of give a false impression or a false image. For more common diseases and more well-known and well-studied ones, we have very good and accurate tests. But for very new occurrences, again, you have to give medicine time to get their stuff straight, essentially, for these new cases. Now, even though it's used a lot in the medical profession, that's not its only use for Bayes' theorem. But again, this is the general way Bayes' theorem has been written in literature. But there's an easier way to remember it than this mumble jumble here. So basically, the way I think about it when I'm trying to remember it is the way Bayes' theorem can be applied to medicine is true positive times the chance of infection over true positive times the chance of infection. Again, these two are exactly the same. So the numerator and the first part of the denominator are exactly the same. True positive times the chance of infection times the false positive times the chance of no infection. Again, false positive, no infection. True positive, true infection, or general infection if you want to say that. So again, there is a sort of repetitious or link here between these two parts of this theorem here. So like I said, trying to remember it using all the mumbo jumbo up here is a little bit more difficult for me, so I try to memorize it using this sort of notation there. Now, like I said, it doesn't necessarily have to be applied to just medical testing. So we'll see an example here where it's still used, just not as a more dire straits. So we have a study here that finds that color blindness occurs in different rates in men and women. So they picked out 100 men and found that six, or not picked out, but based on past studies, we'll say, 6 out of every 100 men are colorblind and 22 out of every 10,000 women are colorblind. Assuming that we have an equal split of men and women, what's the chance that a colorblind individual is male? So this here you have to kind of decipher a little bit. What's the chance that a colorblind individual is male? So that means that if we pick a person and we know they're colorblind, what's the chance that they're a male? So in math terms, we want the probability that you're male given that we know you're colorblind. So let's figure out what we have from the problem here. So we know that 6% of people are colorblind given that they're male. So if you know that somebody's male, there's a 6% chance that they're colorblind. So that's what that 6 out of every 100 means. That's probably my mic that it's detecting. 6 out of every 100 is what it means there. So it also says that 22 out of every 10,000 women are colorblind. So that means that if you're colorblind, given you're a female, there's a 22 out of, or not a 22%, but a 0.22% chance that you're colorblind. So if you're female, 0.22% chance that you're colorblind. So again, knowing how these are written in math terms is kind of a key thing there. So when you're reading like numbers like this, try to keep in your head, okay, what do I know or what do I assume, and what is that assumption trying to tell me? So here you're assuming that they're men because it's out of 100 men, and this statistic is telling you that out of these 100 men, so that's your given, out of these 100 men, 6 are colorblind. So that's where we come up with this decimal here. Same thing for the women over there. It also says you have an equal amount of men and women, so we know that the probability that you're a male is 50%, probability that you're a female is 50%. So again, that doesn't tell you explicitly in the word problem, but you can make that assumption when it says an equal amount of men and women. Chance of male, chance of female are both 50-50. So let's go ahead and apply Bayes' theorem here. Again, I'm going to start off with the way we initially kind of wrote it as, which is, again, the probability that you're male given that you're colorblind. So we're picking from the pool of colorblind people. We want our chance of picking a male. That's going to be equal to the reverse of it. So you reverse your probability, colorblind given that you're male, times the chance that you're male, divided by the chance that you're colorblind. Excuse me, the chance that you're colorblind. Now, once again, we know all this stuff here for the most part. We know that the chance that you're colorblind given that you're a male is 6%. We know the chance that you're a male is 50%, but we don't know this bottom piece. And again, that's where we break it down. What's the general overall chance that somebody's colorblind in the population? If I pick just somebody at random, male or female, I don't care. But if I just pick somebody at random, what's the chance that you're colorblind? Well, I don't know that directly, but I can deduce that that's going to be equal to the chance of me picking a male and colorblind person plus the chance of me picking a female and colorblind person. And then I break these two down into these two categories. So colorblind given that you're a male times the chance that you're a male, colorblind given that you're a female times the chance that you're a female. That gives me my two components here and here. So we end up back to kind of what we did with the medical situation, where again we have this sort of repetition here. We have this sort of repetition here, and then we have the counterpart over here. So the chance that you're a male times the chance that you're colorblind given that you're a male. Or again, you can reverse it like I did here. So since it's multiplication, you can do these in any order you want. So that's why you might see me flip them from time to time. So the chance that you're a male times the chance that you're colorblind given that you're a male over repeat, so same thing on top, plus the female version. So the chance that you're a female times the chance that you're colorblind given that you're a female. So we go ahead and plug my numbers all in here. So the chance that you're a male is 50%, so 0.5. The chance that you're colorblind given that you're a male is 0.06. So this is that 6 out of every 100 males are colorblind. So you're trying to pick a colorblind person from a pool of guys. Well, that means you have a 6 in 100 chance, or a 0.06 chance given from the word problem. Then we repeat that down here. So the first part of the denominator is just a repetition of the top part, plus, in this case, it's just the female version. So what's the chance that you're a female? Well, again, 50-50 times, if we pick from a group of females, what's the chance that we pick a colorblind person? Well, it says here 22 out of every 10,000. So 0.0022, which again, if you don't know where I got this decimal from here, I just took 22 divided by 10,000. And then this, I just got 6 divided by 100. So I just made them into decimal forms. But again, I'm just going to plug this into my calculator here. So get my calculator back up here. 0.5 times 0.06 divided by 0.5 times 0.06 again, plus 0.5 times 0.0022. And we end up with about a 0.964, or that 6 rounds the 4 up to a 5. So 0.965, or about a 96.5% chance. So the probability that you're colorblind, the probability that you're male, given that you're colorblind, is about a 96.5% chance. Which, if you pause and think, makes sense based on what we have in the problem here. So let me explain that here. If 6 out of every 100 guys are colorblind, but only 22 out of every 10,000 women are colorblind, that means if I have a group of colorblind people, there are going to be a lot more guys in that group than there are women in that group, because being colorblind in a guy is a lot more common than being colorblind in a woman. So if I just take a bunch of colorblind people at random and put them into one big group and then try to pick somebody from them, I'm going to have a lot more guys to pick from that group than I'm going to have women. And again, by a factor of a lot. We have out of every 100, there's 6, and here's out of every 10,000, there's 22. So we have a 100 times increase in the number of people, and not nearly 100 times increase in the number of colorblind people in that group. So that's why this is such a drastic chance here, because my group of colorblind people is going to be so heavily skewed towards the male end of the spectrum that I'm going to be very likely to pick a male from that group of colorblind individuals. So something that gets lost a lot in probability with Bayes' theorem is that people tend to lose the link between the forest and the trees. They tend to get so focused in these small little probabilities that they don't kind of take the chance to look back and see if their answer sort of makes sense in the overall context, which in this case, again, it does when you think about what these numbers actually mean. You have a lot more men that are colorblind than women. So if I pick from a group of colorblind people, I'm a lot more likely to pick a man than a woman. If this was like 0.4, then I'd probably be a little bit more suspicious that I did something wrong with my work. So again, knowing how to sort of gauge your work can help see if you're on the right track or not. It's the same thing for the infection too, by the way. So you might think only have a 19% chance of being infected. That's quite small given that the test is 90% sensitive. But again, it's a very rare infection, and we also have a 20% false positive rate to contend with. So given the chance that your probability of being infected in general is very, very low, and the chance that you have a false positive test is pretty darn high compared to the rarity of the infection, or I guess put another way, the chance that you get a false positive is in a sense higher than the chance that you are to get actually infected. that's going to heavily skew the results of the test there, which is why this is such a low rate compared to the sensitivity of the test. The test is 90% sensitive, yes, but given that the false positive rate is so far ahead of the actual general rate of infection, that's going to again throw off your accuracy for your test essentially. So again, it takes a little bit of getting used to for this theorem, but in terms of the actual mathematical numerical part of it, as long as you remember that there's a repetition between the denominator and the numerator here. These first two pieces are just repetitions of each other. So if you can get these down, then all you need to kind of realize after that is that the second part of the denominator is just the opposite probabilities of the first part. True positive, false positive. Chance of infection, chance of no infection. And it's the same true here. We have probability of male, probability of female. Colorblind given male, colorblind given female. So again, if you remember half of Bayes' theorem, you basically memorize it all because the last part of the denominator is just a reverse part of the first. So again, takes a little bit of getting used to. Hopefully this video helped you out. Hopefully it will assist in your studying. If you have any questions, as always, let me know. Otherwise, that is legit.